Now it's time to kickstart the IMSE Days 3.0. We begin with a module concentrating on light, the future of light, to be precise. The module consists of 3 interesting presentations from industry experts, offering you a deep dive into the world of IMSE illumination. First up, we have a joint presentation together with LightWorks called IMSE Illumination and Trends in Lighting. Here at TactoTek, we value building an IMSE ecosystem comprising of a network of IMSE design, manufacturing, material and component providers. And this is where also LightWorks comes in. We are collaborating to develop innovative, novel lighting solutions together. And I'm very pleased to introduce the first presenters of this year's event. Matthias Röhnfeldt from LightWorks.
Hello, everybody.
And Pasi Korhonen from TactoTek.
Hi.
And now, Pasi, the stage is yours.
Thank you, Tua. So, let's walk through what IMSE illumination means, first by comparing it to conventional illumination design, and then see the opportunities it enables. In the beginning, we can quickly review what IMSE can offer to illumination design. Compared to conventional assembly of PCBs, LEDs, light guides, and frames, we can squeeze the design into one thin and seamless part which still can include the same functionality. We can place the LEDs freely to areas where the light is needed, close to the illuminated item. Light is controlled by resin material, film substrates, and inks on A and B films. Brightness and uniformity requires new engineering tricks. Here we have an IMSE design example, a door trim with large area illumination, which we have created in TactoTek. Let's go over the illumination design features and benefits with the help of this design example. First, we have to discuss the main difference between IMSE and conventional technology. In IMSE, the plastic resin is the light guide. This means that the LED and all the light it produces is initially in the light guide. The design task is to keep the rays in the plastic and guide them to needed area. In conventional design, the LEDs and PCB are located outside of the light guide, so the light incoupling needs to be considered. Also, the LED light guide positioning tolerances affect to the efficiency of incoupling. So we see in this picture that the distance between LED and light guides really has an effect on the incoupling efficiency. Let's take the door trim as a design example where we can compare these technologies. In order to build illumination for such surface with conventional methods, we need a frame which is used as a base part of the illumination assembly. The frame holds the light guide that is used to create uniform illumination to the trim surface. The frame also reserves space for LEDs and PCBs which are located close to the light guide. The topmost part is the visual part with decorative surface. In cross-section, it looks like this. Even with tightly packed and optimized design, the thickness of such assembly can be 15 to 20 millimeters. At minimum, 3 separate tools are needed to manufacture the parts plus final assembly to build it up. If illumination pattern needs to be changed, it means modification to the light guide tool where the outcoupling is defined. This means that each illumination variant needs its own tool set. If we do this door trim with IMSE, the LEDs can be placed anywhere inside the part, and everything can be modeled to one part. So there is only one part instead of an assembly, which means that only one molding tool is needed. In comparison to conventional technology, we can reduce the thickness quite a lot. Also, there is a good variability. Changes can be implemented by printing. No tool modification needed. IMSE stack cross-section looks like this. All functionality can be integrated to one piece, where the resin is the light guide. LEDs can be placed to where the light is needed, and there's no need for PCBs. Thickness can be as thin as 3 to 5 millimeters. In this picture, you also see the PMMA layers marked with yellow color that are not always needed, but give benefit in large area illumination. We will discuss about that benefit in next slide. Let's look at the light propagation theory in both technologies. In conventional method, the light guide is surrounded by air, which means that the index difference between polycarbonate and surrounding material is high. The critical angle where the total internal reflection happens is 39 degrees, so that we can keep most of the rays inside the light guide. The light propagation is efficient, but the drawback is the complicated assembly. In IMSE technology for large area illumination applications, where we want to transfer light efficiently, we can use a material with low refraction index compared to polycarbonate. In this case, we use PMMA covering the polycarbonate resin that you can see here in the picture. The index difference is smaller, thus the critical angle is 70 degrees. However, we still get significant amount of light into the light guide. This allows us to create thin and simple parts with illumination and functionality. In conventional light guide technology, the outcoupling is done by 3D shapes on the light guide surface. This is typically created in tool surface, and it means that it's one tool per variant. In IMSE, the light outcoupling is done by 2D printing, either screen or digital printing. The outcoupling pattern can be formed by printed dots, for example, as we see here in this picture. Printing gives flexibility. There is no need for tool changes with variants. The door trim we saw previously with large area illumination can also have different functionality with the same tooling with different print layout. In this example, we have touch buttons with illuminated icons. The user can actually control the vehicle by the door trim instead of only getting information from it. Illumination itself can be done by using the same IMSE stack as in large area illumination example. The light management is carried out by color inks instead of total internal reflection. Conventional electronics create conventional interfaces. For example, creating illumination features with light guides, etc., require a certain installation depth, which often makes the HMI panel thick. Variant management can also be costly. Each cosmetic and functional variant of the same part may require variant-related toolset, which complicates the assembly and even the manufacturing process. Also, as with all electromechanical interfaces, the more interfaces the structure has, the greater the risk in terms of reliability. Dirt can get between the parts in an assembly, which causes not only visual defects, but also functional issues. IMSE parts have seamless single-piece surface that are chemical resistant, which makes them easy to clean. Electronics are encapsulated in plastic, protecting them from moisture and debris. Three-dimensional form enable visually appealing and easy-to-use products. Brand differentiation is as easy as changing the print layout. And from illumination point of view, we can create different illumination features, for example, large area illumination, icons, etc., within the same part with only one tool. Here we have an example of refrigerator control panel made with IMSE technology. Illumination can be used for various functions. The top edge part is used as a status indicator. It can be used, for example, for temperature indication, red for temperature rise, cool white for freezing function, etc. Large area illumination is an effective way to utilize this kind of indication where the light is clearly visible and the color brings the status information. Capacitive touch buttons can also be equipped with illumination. The icons can be hidden when they are not needed, which simplifies the user experience. The refrigerator can be controlled by a slider like this, and its status can be indicated by illumination. As we have seen, there are clear benefits in IMSE technology. In IMSE, the resin is the light guide, and all the light is inside the part. There's no PCBs needed, and LEDs are driven through printed wires. It gives freedom in LED placement and produce light where it's needed. Illumination solution can be integrated to one part. It saves space and eliminates complicated assemblies. And printed functionality. Effective variant management with simple print shades without additional tooling. And now it's time to switch over to Matthias Rönnfeldt, Technical Director of LightWorks. Please, Matthias, the stage is yours.
So thank you, Pasi, for your presentation. So ladies and gentlemen, also from my side and the entire LightWorks team, a very warm welcome to this IMSE Days 3.0 in 2020. Before we start here into IMSE technology, I would like to use a chance to give you a brief introduction about what is LightWorks doing and where are our customers. So LightWorks, with its 10 years on market and 25 employees, is located in Holzkirchen with its headquarters. We have a second office in Ostrava, and we are supporting our customers, and that means the international OEMs and tier sector with light system development. That means we are supporting an operative project management, an optical system development, mechanical integration of these systems, and electronic functionality behind that. And we are pretty proud about our track record, and that means we realized here with our customers together 230 lighting projects over the last 3 years. To give you a better understanding what does it mean and what kind of projects we are supporting, here I will show you a short overview of 3 exterior lighting projects. We have here the BMW X7, which we supported for the OEM side. We have the Porsche Taycan rear combination lamp, which we supported for the series supplier. And on the right side, we can see here an hypercar manufacturer. We did also the entire headlamp development. We have also a lot of interesting interior projects which we supported over the last years. We can see here the upcoming 7 series where we did the concept development. We can see here in the middle the all-new S-Class from Mercedes-Benz where we supported our partners. And on the right side, we can see a pretty cool project from Audi, the Q8, where we supported also the series development for the interior lighting package. So what does it mean to integrate modern and functional lighting into brand new cars? We tried here to bring all these challenges into an overview, and we generated here 3 main challenges, and I will begin here on the left side of the slide. We have challenge 1, and that means we have light and function all over the car. And this gives us here a big challenge regarding the integration point. That means we have to find smart and intelligent ways to integrate here lighting and HMI functionality in places where no light was before. So that means we have a lot of work to do from the integration point of view, and of course we have also a lot of need to have here good interaction with all these stakeholders which are involved in this integration work. So in the middle of the slide, we have the second challenge, more light and function in the same package. And I think when we have a look to new car projects, we will see this already in the cars when we are talking, for example, of the combination of ambient lighting and functional lighting in the same package space. That means here is a big challenge, and also high integration approaches. That means how we are able in the future to pack all these new functions together in one package. And that gives us here also new requirements for heating management, for the optical design of the functions, and the communications interfaces to the car, but also to the end customer. And we have challenge 3, same light, more functionality. It's roughly the same, but here we are talking also about let's say the quality of light again. That means we have more pixel, for example, we have smaller packages, we have also HMI combination with light. And I think we will see, and we saw already in Pasi's presentation, what does it mean when I would like to combine lighting and human machine interface functionality. So here on this slide, I will give you a brief overview of common and also upcoming lighting functions in interior lighting. On the bottom of the slide, we see the well-known ambient lighting and contour lighting functions. And on the top of the slide, we see the rising stars in interior lighting. We see here projection functionalities and surface illumination. And this is one of the topics today, what we would like to talk about. So what does it mean? Surface illumination, and what are the advantages and opportunities for the stylists and also for the engineers by the same time? So of course, with surface illumination, we will enter here a complete new field of creative freedom. We are talking about 2D surfaces. We can talk here about 3D surface, and of course, as Pasi mentioned also before, we are able to illuminate today here also complete new and 3D freeform shapes. And that gives us here also, of course, a pretty nice possibility to generate unexpected lighting effects. And we can push here also all these Chi-Tech approaches forward. And of course, we have also the possibility by using this 3D freeform shape surfaces for the implementation of different functionalities. And here we are talking again about combination of HMI, of ambient lighting functions, of functional lighting, for example, for functions when you are opening the door, and then the car will warn you that there's a cyclist coming in your area. So having a look to the A surfaces, when we are talking about surface illumination and unexpected user experiences and Chi-Tech approaches, then everything should start here from the A surface, because this is what the end customer will see. And here I will give you also a short introduction about a possible A surface for surface illumination. We can talk here about natural materials, for example, real wood veneers or stone veneers are in trend now. We see here in the middle of the slide leathers and artificial leathers, textiles, which can be very well illuminated. And last but not least, on the right side, we see a pretty cool example for highly decorative plastic surfaces. And of course, also this kind of surfaces are pretty cool to illuminate. So to give you also a first impression how it could look like in the future, we have here 3 examples for these kinds of materials which are illuminated. On the left side, we see here an illuminated rearwood veneer. In the middle, textile with an B surface covering, and on the right side, we see a decorative plastic surface, or two different decorative plastic surfaces which are front illuminated, but I think you can see here what's possible with the right surface and also with the right structure on the surface. So after talking about a surface, of course, we have also to talk about the technical approaches behind that. And here I will give you also a short and brief introduction in technical approaches to generate surface illuminations. Starting here from the left side, we can see a pretty simple approach. We call it waterfall illumination. That means I am using here simple LED array or also a light guide to illuminate the A surface, or directly illuminate the A surface here from the top. You can do it also from the bottom or from the side, but this gives you a pretty nice approach to have an easy surface illumination. In the middle, we see the area light guide approach, the classical area light guide approach. This is a little bit more complicated. Here we are talking about transmissive light approaches. That means I illuminate here the B surface and push the light through the A surface. And therefore I am using a surface light guide or a segmented surface light guide. This is a little bit depending on what we have to illuminate. When we are talking here about lighting dynamics, for example, then I would use maybe a segmented light guide. But as you can see here, the light guide is shown in light blue. Then we have here in yellow a certain covering on the B surface of the cover, and this will gives you on the end the pattern what will be illuminated. And here I'm using also LED array or a light guide to illuminate the area light guide. The third approach is a little bit more electronic driven. Here we can see a 2D LED array with a lot of LEDs behind the A surface, and this gives you, of course, the possibility to generate here high complex lighting dynamics, for example. And this is, of course, also a transmissive illumination approach. And on the right side, we pick up again the TactoTek approach, which was pretty well introduced from PASI. Here we can see one of the biggest opportunities and advantages. It's pretty thin, it's pretty compact, it's pretty integrated, and of course with this TactoTek approach we can also find very good solutions to generate here surface illumination and complete new user experiences via this approach. So on this slide, I will give you also a generic comparison in between these four surface illumination approaches. Of course, as I mentioned before, the waterfall illumination will be easy to integrate. We have no big package restrictions behind the surface. The electronics are pretty easy. But of course, this waterfall approach will have some restrictions in lighting dynamics. This is changing a little bit in the two approaches in the middle, the transmissive illumination approaches. But as we mentioned before, here we have bigger restrictions when we are talking about packaging and light system integration. And looking to the direct matrix illumination, we can see here also the complex PCB behind the illumination, and therefore, of course, we have bigger challenges when we are talking about electronics. That means also from communication side of view, also about thermal management. But of course, on the other hand, we have here also more or less in this example, we have here a pixelized system, yeah, with a big amount of opportunities for lighting dynamics. And the TactoTek approach is more or less a mix out of all the cool opportunities. We have small package requirements, as Pasi shown us before. We have also less electronic restrictions in direct comparison to the direct matrix illumination. But we have here the big advantage that we can generate here lighting dynamics and HMI functionality in one highly integrated system approach. And this is for us here the biggest advantage. Giving you here also some visual impressions about what we are talking here. We had here the opportunity in LightWorks to implement the all new TactoTek interior mock-up into our virtual development platform. And therefore we have the opportunity to show you here the first pictures which were generated with our physical based warm rendering. Here we see the mock-up in cold appearance, and now I will light it up here for you. And here you can see the in the left side of the picture, you can see the illuminated door trim, what Pasi mentioned before, together with some well-known control lighting functions, and you can see how cool it looks in warm appearance. And I will show you the door trim also in a more detailed look. And I think one of the biggest opportunities when we are talking here about A surfaces, of course, that this can be changed really easy without big tool changes, or completely without tool changes. And this gives us here and also our customers a lot of interesting opportunities when we are talking about diversification, about different additions in cars, and gives also the end customer the possibility to have here individualization of interior trims and design in general. And on the end, I will show you also a short animation of this door trim. And here you can see we implemented here also an lighting effect into the door trim. And I think this is a good end of my presentation and gives you here also a good feeling what is possible with this TactoTek system approach and with TactoTek illumination design in general. Thank you very much.
So thank you, Matthias, for the impressive presentation. So as a summary, I would like you to remember this. IMSE differs from conventional illumination designed so that the LEDs are in the light guide with printed wires. The LED positioning is free and there's no need for PCBs. Index difference need to be created by material, not air. Illumination feature can be integrated to one part instead of an assembly. Outcoupling and artwork design is done by printing. It enables flexible localization and variant management. So this was my part, and now I will hand over to Tuva. Thank you.
All right, thank you, Pasi, and thank you, Matthias, for your excellent presentation. And next up, we have the live Q&A. All right, so now it's time for the live Q&A with Pasi and Matthias on the line as well. And while we wait that they they joined the session. There is Matthias. Hey. There have been questions about if we can share the slides afterwards, and you will have access to all the content after the IMSE days, and you can also view all the videos on YouTube after the event. So, hello, Matthias.
Hello.
Hello, and do we have Pasi on the line?
Yes, I'm here.
Okay, hey, Pasi. So first up, about the live Q&A of the questions. Thank you all for your questions and keep sending them in. We'll try to take as many of those as possible. So first up, this is for Pasi. How do you handle light leakage without specific light guides?
Okay, we manage light leakage with material selection and also with inks. So we can use low reflective inks where we don't want the light to be bleeded to another icon. And we are also continuously working on new methods, new more effective methods to prevent light leakage.
All right, thank you, Pasi. And are there some specific limitations for the component placement?
So I guess that's for me still, but yeah, from illumination point of view, there are no limitations. Just to make sure that we don't get hotspots in the icon area, and we have also methods for that. So basically, the LED placement is pretty free for illumination.
Okay, Matthias, do you have viewpoints?
Something to add?
It was pretty.
I think this light bleeding and light leakage topic is, of course, obvious. And one topic or one solution is, of course, to use here specific materials, specific inks to avoid this. And of course, what we all have to learn is that with IMSE, we have also the possibility to have a complete, roughly complete free positioning possibility of the LEDs. And this gives us also a new dimension of design freedom to have the right position of a LED to avoid light leakage also from the approach that we can generate here the right direction of light beam in comparison to classic approaches.
Okay, thank you, Matthias. Then we have a question regarding if we believe the IMSE will be applicable for Japanese vehicles, meaning that the technology can meet the requirements of the Japanese companies. So, Matthias, what do you think?
I think there should be no limitation. I'm not sure if there is a difference in between Japanese and Europeans or US car requirements or application requirements. It would be new for me, so I'm pretty curious.
Yeah, absolutely. And then I think this is more for Pasi. Now, what is the illuminance value, candles per square meter, that we can achieve through the TactoTek approach?
Yeah, we can reach anything between, let's say, 5 candles per square meter to 5,000 candles per square meters. It's very application driven. So if we want to have a mood light or something, then the luminance is lower. And then if we have to indicate something that the user can clearly see what's happening, then the luminance requirement is higher. So then the 5,000 candles per square meter is needed.
Okay, thank you, Pasi. And then here's one question that I can actually take regarding that. What is necessary to be your production partner? So TactoTek licenses, or we have licensing packages that are targeted for both design and engineering companies and mass producers. And from the production side, the full IMSE production line consists of screen printing, SMT, thermoforming, and injection molding. And if you want to receive more information on this, please contact sales@tactotech.com. And then we have question about how to spread the light evenly to avoid hotspots.
Yeah, there are methods to prevent hotspot by inks on A film, so that we can play with transmittance of the ink that the light is coming through, and then also we can play with reflectance on ink on B film, so we can quite effectively take the hotspots away and make sure that the uniformity is okay.
Okay. Well, this is kind of related to that about the thermal management with the IMSE products, for example, in the lighting application. So how to get the heat out of the hotspots.
Yeah, we first of all, the power levels, we can play with those, and then we can also use some thermal management materials to get the heat away from the LEDs.
And maybe to add here something, it's it's always about a trade-off. Yeah, we don't have, or let's say in general, lighting system development approaches, we are very tightened with packaging restrictions. And here, one of the big opportunities is to have all integrated in one part, and that gives us also the opportunity to use maybe more LEDs also in places where it's not possible today with classical technical approaches. And this will allow also the specific and local heat input in the assembly. And therefore, of course, we can smooth here a little bit the complete thermal management approach. And this gives us here also advanced possibilities to handle thermal management in general.
Right. Thank you, Matthias. Then question about the light bleed, how to eliminate the light bleed from one icon to another.
And maybe this is a little bit connected to my last, or my second last answer, to say, okay, today we can, it's possible here with IMSE to place also LEDs in a more intelligent way. And if I have it's always depending how close are the symbols, but if there's a little space in between, of course I can put there also two LEDs back to back, and therefore I will avoid bleeding anyhow, because one beam is looking to the left, the other beam is looking to the right. So this is one of the magical approaches here in between, that we have to understand all these new design freedoms, also for us from LightWorks. Yeah, new approaches, also new mindsets.
Exactly. How about Pasi, about the light bleed?
Yeah, it's the material selection, so we can select the material in between the icons that is not very good light guide, and also the ink selection between the icons can be, we can use black ink between those two icons, and we can neglect the light bleed.
All right, thanks, Pasi. Then we have a question about the inks, and I can take this one, that what kind of inks we use. We have at TactoTek tested dozens of different functional ink families, and these functional material combinations can be found in the TactoTek licensing packages. And like I said, you can find more information about those from our website and contacting us through there. And then we have a question on what is the lead time with IMSE light compared to light guide design?
From developing time. talking from developing time in comparison to normal light guide design.
Yes.
Yeah. Okay. When we are talking about light guides, and here today we are talking about surface illumination. Of course, there's some more things to do on the end, but I think it's comparable. It's always depending on the use case, on the complexity of design as usual. Yeah.
Yeah.
I can have also very, very complex light guide designs. Yeah. We have to understand the concept, and then I think it's pretty comparable to classical approaches.
Yeah, if all the design is based on simulation, then I guess that process is pretty similar. But in the production phase, maybe if we want to make some changes, we can do the print round pretty quickly. So I guess with the same tool, we can try different things.
Yeah, no big tool changes.
Yeah.
Yeah.
So I would say that it's pretty similar to conventional, or even quicker from the production point of view.
Yeah, exactly. Then we have about color mixture. Which distance a color mixture is achieved?
Yeah, this is also application driven. So if we can utilize the indirect lighting, then the color mixing can be somewhere between 10 to 15 millimeters. What do you think, Matthias, from your perspective?
Yeah, I'm pretty agree with you. It's depending also on the use case, and we can play here also with different inks, for example, to manage here the color change. It's depending on the general shape of the part, which will give us opportunities or also some restrictions. Yeah, we have here different parameters to play. It's not just a light guide without structure on the end.
Yeah. So basically, it's quite difficult to say a number for the. Yeah. It's a very design-driven, application-driven.
It's also very difficult to tell a number with a standard light guide.
Okay.
On the end.
Yeah.
Then about the typical assembly materials and processes that we use for attaching LEDs. What are the typical assembly materials and processes?
Is it for IMSE or conventional?
I guess for the IMSE.
For attaching LEDs, we are using the conductive inks and adhesives. So that's basically what we do.
Yeah, thanks, Pasi. And then we have quite a few questions here about the life cycle of IMSE and about the materials or the lifetime of the IMSE parts and materials. So you will hear more about the IMSE material verification in today's session with Covestro about the how IMSE drives plastics development. So our Paavo will tell you more about the IMSE material verification there. And you can also head over to a YouTube channel and watch a webinar on the material verification as well. All right, thank you, Pasi, and thank you, Matthias, for your Q&A session. We have to now move forward in the program.
Thank you.
All right, thank you, Tua.
Thank you so much.